It's only a couple of minutes after the hour, but let's start and let Ned have more time than if I delayed his introduction. Anyhow, Ned Wright is speaking to us today, come here all the way from physics and astronomy. And you've seen, I think most of you, his abstract telling you what at least in capsule form, what the missions and the proposal are. He joined UCLA in '81 and has been involved in a bunch of space missions, and most recently the one, at least the one I know about, is the WISE mission, which is an infrared mission, and which for a meteorite researcher is very enjoyable because it's discovered more asteroids, I think, than any other mission by orders of magnitude, and is in the long run going to be very important for people like me who want to know where the meteorites come from. So, Ned,
okay, thank you, John. I'm going to be talking a little bit of a historical review, so let's go back to 1973 or so. So there I was, had a lot more hair, a lot more beard. And that's a 40 inch, 102 centimeter far infrared telescope that flew on a balloon. And those who've suffered through Palestine, Texas will recognize the launch truck known as Tiny Tim that's holding this 2-ton telescope up. Now, during flight, I jumped off just before launch, so.
How long was the flight?
Just a night, so this is not an ultra-long duration thing. So to analyze the data that I finally collected on the fourth flight, I needed to calibrate, and of course the only objects bright enough to calibrate in those days were planets, but the previous observations of planets had been all screwed up. They had assumed that Mars was always 235 Kelvin when figuring out the brightness of other planets. So I had to do a Mars model, and then I published that. And it turns out that the JCMT uses that Mars model internally in its calibration system. Now, I never get cited for that, but when the table I had published ran out, then I had, got a request from them to extend it. So now it's extended to 2107. I assume by then the JCMT will be off Mauna Kea. And so we did observe some other planets, so we got a brightness temperature of Venus and Jupiter. And Uranus turns out does not have an internal heat source of any great magnitude. Neptune's about a fairly substantial fraction of infrared energy from Neptune is internal, and about half of the infrared energy of Jupiter is internal. And just to get on to asteroids right away, I looked at Ceres. So considerably before Don looked at Ceres, so there you go. And then the first space mission that I was working on is COBE, and so that's not a penny, that's a Nobel Prize next to it, but the Nobel Prize winning instruments were the DMR and the FIRAS, and not the Derby, the diffuse infrared background instrument. But the diffuse infrared background instrument was quite a tour de force, so it had 10 bands looking at an off-axis telescope with lots of sky stops. So this actually could be scanning along, and then 1/8 of a second before it crossed the moon, it's still, delivering pretty good data. And then it saturates when it hits the moon. And it did scan right over the moon. That's the beam size and shape of the Derby compared to the moon. And this beam would swing around in a circle that would advance as the satellite goes around in its orbit. And so it scanned about half the sky every orbit, every hour and a half. So of course it scanned planets all the time, very frequently. And there is a data product that's at the Lambda site if you want to look, the Derby SSO, Solar System Observations file. And it's got the brightness in all 10 bands of solar system objects. So you have Mars and Jupiter. So Jupiter, Mars, Saturn, And then these fainter ones, Uranus. Now the thing is, this only triggered when there was a solid detection, at least one band. So this is not really the best way to determine the brightness of the planets if it's not triggering every time. So like for Uranus, you can see that these are probably noise fluctuations upward. And then the average of that, so you get Jupiter and Mars. So I think this is probably the last experiment to look at Jupiter that didn't saturate on Jupiter. But it's certainly extremely insensitive. So I was able to observe Jupiter on scale. Okay. WMAP. So WMAP won the Breakthrough Prize just recently, and that's for the CMB work. But WMAP was launched in 2001. COBE was launched in 1989. So this is absolutely calibrated. So actually, by observing how the CMB dipole varies over the year, we know how fast the Earth goes around the sun very precisely. You get an absolute measure of the CMB dipole, and then you can compare everything else to that. And so it's got a big circle. The COBE scan pattern here, this is a equal angle circular projection around the anti-sun direction. So the red is COBE, the green is MAP, as it was called before it was renamed in honor of Dave Wilkinson. And so this means that it observes the planets many, many times. And so we use that to figure out our beam shape. So Jupiter, Saturn, Mars, Uranus, Neptune. And we had to take out those planetary blips before we averaged the CMB data, so we need to figure out where they were.
Did it saturate on Jupiter?
No, so I was wrong.
I thought you might be.
It's always possible to have an insensitive instrument. So this is the average W-band brightness for an apparition compared to the Mars model, my Mars model, which is really antique and not very good, but seem to match the temperature variations quite well. There's an emissivity correction here of -6%, and then with the other bands on Mars, you can see that continues to the lower frequencies. Okay, so the next mission I wanted to talk about is the Spitzer Space Telescope. And this has the, it was launched in 2003, but among space missions, this has the honor of being the first one I worked on. So this is me at the Ames Research Center back when the Spitzer Space Telescope was headquartered there. And you can see a number of luminaries in infrared astronomy, our own Eric Becklin here, Fred Gillette. And this is my thesis advisor, Giovanni Fazio, who is still going strong. Okay, so we were trying to figure out what instruments would be good to put on a space telescope. At that time, it was known as the Shuttle Infrared Telescope Facility, SIRTIF, which later became the Space Infrared Telescope Facility and finally became Spitzer. So Spitzer observed minor planets, and I got a bone to pick with the TAC. So Peter Eisenart and I had proposed that we should take all the NEOs with good orbits that pass through the Spitzer zone of availability and observe them with all 4 bands of the IRAC. And then we got turned down because we just said, well, we'll just look once and it's not going to be too bad. And the TAC said, but they have light curves. Well, it turns out the light curve's not a very serious objection. So everybody thinks about it, but if you have the median amplitude light curve in the light curve database for asteroids is 0.4 of a magnitude. Now, nobody's going to be spending a lot of time on asteroids that have a very small light curve amplitude, so that's no doubt biased high. And 0.4 of a magnitude is about 36%, and that's from peak to valley. So the actual RMS error that you get is that 36% divided by the square root of 8. So it's just a little bit over 10%. So it's actually a pretty small effect. So because we got turned down for that, the next year we proposed getting 3 observations to beat that down by square root of 3. And then we got turned down again for using too much time.
That wasn't very nice.
No, well, this was annoying. But anyway, so then the Spitzer ran out of helium and you lost the 2 long wavelength bands of the IRAC and everything on the MIPS and the infrared spectrometer. So we didn't propose again, but Dave Trilling out at NAU did. This is the Explore NEOs proposal. Basically the same idea. All the NEOs that were passing through the zone of availability would get observed by Spitzer, but only with 2 bands at 3.5 and 3.6 and 4.5 microns. And then here's their first paper. So one of the main conclusions they had is that there's a trend in albedo. So small objects don't have low albedos. Now, of course, if you've ever had a selection effect, you know that could very well be a selection effect. But that's the published result in 2011. But we now got to the WISE project, which John kindly described. So this is a very small telescope. It's half the diameter of Spitzer, 40 centimeters. And it has 4 imaging channels when it was launched, covering 3 to 25 microns. And with the cryogen, which was solid hydrogen, we could keep the telescope below 17 Kelvin and the detectors down around 8 Kelvin. And so we were in a sun-synchronous orbit that put us orbiting around the Earth like this with the sun over here. And so that means we could always look around the Earth, look away from the Earth, and then have the sun off to the side. And then we had a sunshade that protected us from the sun. And so we can do that. And the basic problem is that we have no propulsion. So we're operating still, but the orbit is decaying, and therefore it's precessing a little bit faster than 1 cycle per year. So instead of now being perpendicular to the Earth's own line, we're now, the orbit is shifted by about 24 degrees relative to that. So this is probably the last year that WISE can operate. So why do we want to go into space and go to all the trouble? Well, the basic reason is that the background from space, this is the source of photons that produce your noise, is 3 million times less than the background that you would get from the ground. And so I've done plenty of mid-infrared astronomy, in the thermal infrared at 10 microns from the ground, and it is tough. So you have to have a chopping secondary and wobble and all that and go back and forth and integrate for long times. But in principle, you can do it. So actually, if you take what WISE can do in a minute, the 10-meter telescope can do that in an hour. So that's the kind of scaling. So going into space pays off and lets us scan fairly fast. So we actually do, every 11 seconds we get a picture, go around and lay down a continuous strip of pictures all the way around that circle perpendicular to the Earth's sun line. And so we have about 10% frame-to-frame overlap, so sometimes you see an object and then you see it again 11 seconds later, but usually you have to wait a whole orbit, and that's about 95, 96 minutes before you see it again. But then you see it again for about 12 times. For asteroids, it depends on how fast and in what direction they're moving. But after 6 months, we'd covered the whole sky, and then we just kept going around again. And the cryogen ran out after about 8 months. So after that, we only had 2 bands, not the 4 bands. So we only had the 2 bands at 3.4 and 4.6 microns, very similar to the warm Spitzer. Now, the reason we did this scan survey the way we were doing it, the strategy, we could have taken images, the 12 images, say 11 seconds apart, all of the same field to get the redundancy we want. But then asteroids would not move enough to be obvious. And we really wanted to be able to tell the difference between an asteroid and a star or a galaxy. Because as good astronomers, we wanted to get the vermin of the sky out of our images. And we'd all suffered with the Air Force Cambridge Research Lab, which is now called the Air Force Geophysical Lab, infrared sky survey, which came out in 1975, and that was based on rocket flights where they didn't have, you know, a few hours to wait for asteroids to move. And so they had sources in there that you couldn't identify with any optical source, and therefore it was a really fascinating object. But when you went and looked for it, you couldn't find anything. And those were mainly asteroids.
But there were some very interesting non-asteroidal objects in the
Yeah, I mean, there are definitely interesting objects, but you know, 90% or more of these infrared-only objects turned out to be asteroids. So WISE gets 12 exposures spread out over about a day, so asteroids are clearly identified by their motion. And this is, Joe Massiero made this little movie. Very crude, very early days. This was before we started the official survey. But the red color in this is the 12 micron channel on WISE. And then these are 5 main belt asteroids with diameters given here that are moving around from orbit to orbit. So there's 4 frames in this movie. So the total time span is about 4.5 hours between the first and last frames. And you can see there's a number of stars and galaxies that are fixed, but they're mainly showing up at the short bands, 3.4 and 4.6 microns. Now there's one galaxy that's consistently in the same spot on the sky here, but there's 5 obvious asteroids. So at 12 microns, asteroids are really bright compared to stars and galaxies.
What's the right thing on the far right?
You mean the little streak?
Yeah.
That is what is known as a cosmic ray.
Oh my goodness.
So,
Little green thing that's pop up, there's that one. The little green dot, yeah, right there.
right there.
Up right above the corner.
Well, that's a blue dot. Oh, there's a green dot.
Yes,
Okay.
green dot.
Yeah, that's just a glitch of some kind.
That's a green dot.
Yeah, so the reason that, the other reason we wanted 12 exposures is that, you want to be sure the object repeats and repeats and repeats in the same place before you publish it as an infrared source in a catalog. So the WISE catalog has 750 million sources in it, and they're all quite reliable. They were seen in the 12 exposures and not moving, or maybe moving really slow because you can get proper motions of stars, nearby stars. But all these things that are moving fast between, from orbit to orbit are asteroids. And our original plan was to dump those out on the ground and ignore them. But Amy Mainzer got some funding from NASA to actually analyze them. And then we built a system called the WISE Moving Object Pipeline System, WMAPS, that is like the Pan-STARRS Moving Object Processing System. And so it looks for objects that are moving across the sky, more or less in a straight line at constant angular velocity.
Must have something to do with ecliptic latitude too. I mean, see.
Oh, this is on the ecliptic. Well,
Yeah, I mean, so like your survey and the AFGL survey there, I mean, if you added the ecliptic.
Yeah, but you know, both AFGL and WISE were trying to be essentially all sky. So AFGL would launch a rocket flight and then scan the sky that was available overhead at that time.
Yeah, I'm just saying the contamination must be much less once you get out of it.
Oh yeah, but the density of galaxies isn't any higher. Okay, so here's Amy Mainzer. And this is just a little illustration of the power of infrared observations to see what's hot. So this is ice water and this is coffee. But the basically, we're looking at infrared light from the asteroids. It's 20 times longer than the visible wavelengths. And it's most of the power from an asteroid is coming out in the infrared because asteroids are dark. So the albedo of an asteroid gives you how much it reflects. But even if you have an albedo of 20%, which is pretty high for an asteroid, because of the phase function, the bond albedo, which is the actual percentage of the light that's reflected versus absorbed and irradiated, is only 8%. So you're always getting 90% or more of the total power coming out in the infrared. So you have at least 10 times more power in the infrared than in the optical, and the photons are 20 times less energy. So you have at least 200 times more photons from an asteroid when you're looking in the infrared.
Why are they warm?
What?
Why do they do that as opposed to an asteroid?
What? Look for them?
No. You're detecting them with them.
Yes.
And they are giving off heat.
Yeah, they're giving off heat, but they're giving off heat because
Why are they
they're
giving off the heat?
rocks sitting in sunlight. So just like the Earth is the third rock from the sun sitting in sunlight, that's why we're 300 Kelvin. And if you have a small rock sitting in sunlight, it's also going to be a few hundred Kelvin. So now asteroids generally, especially near-Earth objects, but even in the main belt, have a bimodal albedo distribution. So you get some dark ones and some light ones. But this is misleading because this is actually the light ones that you have, and the dark ones are like, you know, really, really black. So here's an example of why you want to survey in the infrared. So here's two asteroids that are equally bright in a ground-based survey with 1 arcsecond seeing. And then if you actually had a perfect telescope with resolution better than a milliarcsecond, you could see one was large diameter but dark, and one was low diameter but bright. And then if you look in the infrared, which one's going to be hotter? Well, actually, the dark one's going to be a little bit hotter. You know, it might be doing 97% of the sunlight hitting it instead of 90%. But the big effect is that it's a much larger solid angle, so when you look at it with a telescope with 6 arcsecond resolution like WISE, you see the big dark one, and you can generally just pass over the small light one. And if you're interested in the hazard to the Earth from asteroids hitting the Earth, and there was an interesting talk last Tuesday about asteroids hitting the Earth, you want the big ones. And so here's just another illustration. So you can always tell when it's official JPL product, you know, they have good art and stuff, you know, versus my own simple-minded illustrations. And of course, comets show up real good too. So this is Comet Garad here. And you'll notice it's very red because it radiates a lot more infrared than short wavelength, whereas the red giants, red stars in a globular cluster, look blue to WISE. All stars look blue to WISE because we're way off in the Rayleigh Jean's tail for anything that you would call a star. And so when WISE was going with all 4 bands, it was just an asteroid machine. So this is the total number of observations reported to the Minor Planet Center, nearly 4 million from WISE, and then 1 million from the highest production ground-based survey telescope. So we have measured diameters for more than 150,000 objects. And so as a result, Joe Massiero could come up with this plot. So this is a little illustration of the albedo. Yellow is lighter than dark blue. So albedo versus the semi-major axis and eccentricity of asteroids. So you can see the Kirkwood gaps very clearly. But there's a trend, and in the outer main belt you have more dark asteroids. So lots and lots of albedos, and the IRAS survey did about 2,000 asteroids, but we've done a lot more. And when we actually survey for asteroids in the infrared, these are the WISE discoveries in red here. Most of the ones we actually find with WISE have quite a low albedo. Now the previously known objects, there's some sort of discrepancy between the picture and the label here, but it's the green, and that's much less peaked at low albedo. So if you just go with previously known near-Earth objects, you get a deficit of low albedo ones, which is not at all surprising if you're using an optically produced list of objects, which is what Spitzer was doing in the Explorer NEOs paper. So the result from the WISE survey is that you got lots of low albedo objects at low diameter, and there's no trend of the albedo with diameter. And you can see that better here. So this is a running median of the albedo. And the median albedo is about a little over 10%, 12, 14%, which is what people usually use for converting optical magnitudes into brightness, but there's plenty of very low albedo objects, so you can make a big error if you just go with the median. So a good model for the albedo distribution is a mixture model of two Rayleigh distributions. Doesn't mean it's right. All models are wrong, but some are useful. So this is a useful, analytically easy to evaluate distribution of NEO albedos based on the Neowise observations. Now this particular chart has 2010 AB78 marked in there because that was the first NEO that WISE discovered.
And what's zero phase mean?
Well, zero phase means that the, so I'm looking at the sun now. Zero phase means you're looking right down the line between yourself and, so it's where you get the retroreflection. It's like a, when you're looking at the full moon. Okay, so half moon is 90-degree phase, full moon is zero phase, new moon is 180-degree phase.
So the phase is defined with respect to the Earth, and the Earth is
The phase angle is the sun observer target. That angle.
sun target.
Yeah, sun target, STO, that's right. Okay. So you have two peaks. The bright ones are about 17% albedo, and the faint ones are about 3% albedo. Now I like plotting it this way because it makes this peak look huge, but the actual integral in here is only 25% of the total. So we're not totally off by using an optical estimate of how many asteroids there are, but we won't be finding the dark ones. So when I was preparing this talk, originally I was scheduled at February 1st. And so on February 1st, JPL's Sentry website said that the most hazardous asteroid was 2010 GZ60, which I had never heard of. So I went and looked it up. Turns out WISE discovered it, and then it got no follow-up. So it's a WISE discovery with no ground-based follow-up. And, you know, Sentry was saying over the next 100 years, there's 475 times when it might hit the Earth. Didn't sound right to me. I actually inquired about that, and eventually they followed up. So now it's not reported anymore, and that's a good thing. But the so the cumulative probability of an impact was 5 parts per million, and the it's pretty big. So if it did hit, it would be bad. That's why it's the most hazardous. But it's not really the most hazardous. But what's the list now? So this is showing only the most recently observed in the past 180 days. And here we have 2018 EB is the most hazardous, which was just announced by the MPC on Tuesday. And it's a WISE discovery. So the, you know, it's listed here as 160 meters. It's probably a little bit bigger than that because of the range at which it was seen by WISE. So it's got 2.3 part per million chance of hitting the Earth, but it's not as big.
Are you able to connect these observations with the primary mission phase?
Not yet. Okay, so if we go back a year, you have uncertainties that are thousands of arc seconds, so we can't do it yet. So, and there hasn't been any linkage to a tracklet reported back then, at least not yet. So we'll have to see what happens. And then also the third place here, 2017 SH33 is a WISE only object. So that was discovered by WISE, never got any follow-up. Orbit's not yet terrible, but it did not get follow-up.
What is the reason that there's no follow-up?
Probably because they're dark.
So you can't get optical.
Yeah, so there's a lot of observers that like to follow up and look at the near-Earth object confirmation page. But, you know, a very good setup might be a 40-inch telescope. It's not a huge telescope. And so looking for an object that's 21st magnitude is within their grasp, but if it's dark, then it's 23rd magnitude, and it, you know, gets to be too faint. Well, there's that. And a lot of the, you know, this one is almost full moon. So when WISE, in the cryogenic phase of the mission, when we were more sensitive with the 12 micron channel, we were just discovering a huge number of asteroids, you know, new moon, full moon, because we were just way ahead of the ground-based observers. But now the ground-based observers are about as sensitive as the warm WISE, except during full moon. So they shut down during full moon, and you know, we just keep plowing along.
So which fraction of the original discoveries is considered lost?
Well, considered lost, you know, probably a fair number are, you know, it's hard to say. But I'm going to show you one that's not lost, and it scares me, but it's not going to hit us in the next 100 years, so it's not on Sentry's list. So this is one I count as the most hazardous that I know about, and it's got a, see, it was recovered by Dave Tholen in 2013, so 2010 to 2013. So it's got a well-determined orbit now. And it's also got a pretty well-determined size. It's about 600 meters and albedo of 2%. So it's really dark. And so I estimated that it weighs 200 megatons. And the other thing is it's got a high eccentricity and inclination. So when it gets close to the Earth's orbit, it's moving at a considerably different velocity than the Earth. So there's 29.5 kilometer per second V infinity. And so that's an awful lot of kinetic energy, and that's what we care about for the collision hazard. So it's equivalent to 24 billion tons of TNT.
For comparison, what was the
Oh, for comparison, okay, well that one's a lot more. The Yucatan Peninsula was estimated at 10 kilometers. And so say 1,000 times more.
Compared to Chelyabinsk.
Chelyabinsk is half a megaton. So Chelyabinsk is 50,000 times smaller than this. Okay, the other thing is that after the recovery, we could determine accurately the minimum orbit intersection distance, which is only 0.001 AU. So the orbit of this guy and the orbit of the Earth get very close together. So it's just a question of when the longitudes will line up just wrong. And then it'll be very close. It'll be pretty close in 2082, but it's not going to hit us. So that's good. And it is pretty big, and we can try to model it, using a thermophysical model, and we get pole position map here, sort of like a 45-degree sun latitude to get the temperature right, more or less, and diameters around 600 meters. Okay, I'll show you another version of that later. And so this guy's way down here in the dark peak. Okay, so that model that I'm using is the famous golf ball model. So it's covered with hemispherical, well, not hemispherical, but spherical cap craters. So these are not quite a full hemisphere. And for that particular model I was showing you, they were maximum slope of 45 degrees. But the surface is totally covered with them, which is not what you have with a golf ball. You actually have flat spaces in between. And then the model's pretty general. It can do any convex shape, as the only concavity can be the craters. Okay. So there's another model that people like to use called the near-Earth asteroid thermal model, which has a beaming parameter, which actually is reflecting the fact that light is typically beamed back towards zero phase. Okay, so you get more emission at zero phase angle than you expect. And that is like a retroreflector. But typically the values for the beaming parameter are bigger than 1, which means you have the opposite effect. The light's going somewhere else. And I have my problems with the near-Earth asteroid thermal model, but it works remarkably well. So here's the what I just said. Well, the NEOCam is the infrared phase curve for the NEOCam is given by this black curve, and for the rotating cratered thermophysical model, but with the rotation very slow, so that doesn't count, then you get this curve. And then these are some very old whole disk measurements of the moon. So David Page will remember that I was asking him if he could simulate whole disk measurements of the moon, but it seemed like a pain in the butt. Anyway, and compared to the optical phase curve that's typically used is this G equals 0.15 curve. It falls very rapidly going away from zero phase. And that's sort of the full moon opposition surge kind of thing. So we got these craters, and they totally cover the surface, and then the thing's rotating. And so this is a crater, and the thermal map of the crater is a function of time. And so the crater's at latitude 19 degrees, the sun's at latitude 30 degrees. You can see the sun rise in the east and then hits the western slope and then sets in the west and illuminates the eastern slope at the last bit. And then this just shows how carefully or how crudely I space out the panels. I use a 512 rectangles to cover the surface of the sphere. And for each one of those, then I figure out the temperature distribution for one crater and then use that. Okay, but now, what's currently going on? So WISE is still observing. So we're out past 2018, And we were turned off for 2.5 years, which is too bad. But we are now doing Neowise observations. So this is the Neowise Reactivation. So we're still observing. And that means we can do things. So, you know, we discovered 2015 QM3, which is an A10 asteroid. So it's got an orbit that's smaller than the Earth's orbit, period shorter than a year. And those of you who know your half months recognize it was discovered in August. But because it's an A10 asteroid, you know, it spends most of its time in close to the sun. We saw it when it was perpendicular to the Earth's sun line. So it had to be perpendicular to the Earth's sun line earlier as it left the sunward side of the sky. And so that was going to be in July. And then at the time, the uncertainty in the orbit was pretty small, about 30 arc seconds. So I stacked frames, and at 4.6 microns you can see something there, and at 3.4 microns you don't see anything. And then I could do the same thing a half a day later, and again you see something off at the left edge of the uncertainty ellipse. And so that was 2015 QM3. Seen again, we reported that to the Minor Planet Center and reduced the uncertainty for the reappearance, which is going to be this summer, by about a factor of 3. And we get some estimate of where the rotation pole is, but it's pretty crummy, and we got a diameter. It's a little over 200 meters. But, you know, I mean, one problem with Neowise is we don't have observations near the peak of this curve. So it's very critically dependent to get the temperature here. And with the 3.4 micron band, you can see that there's some reflected light coming in here. And so that introduces more uncertainty. Okay. Okay, this is another little NEO. 2009 FD. WISE didn't discover it. It actually got observed by radar, and it's a binary. But WISE has seen it 3 times. Maybe it's seen it again. I haven't checked again. But it's a low albedo, so 6% albedo. Diameter is just over 200 meters. And this is good to have a low albedo because it means the 3.4 micron is more useful for telling you how hot the surface is. So we can actually estimate the surface thermal inertia, and it's running about 2300 in MKS units, which means it's kind of a rocky surface. Pretty high. Okay. So basically, this thermophysical model, as it's now running, has got 8 parameters. So typically, you don't have that many data points, and you have to use priors to constrain all the parameters, or as initial guesses on all the parameters. But you usually get a pretty good diameter out. So in this case, you get a ridiculously good diameter out, at least internally. It's only 3 or 4% error in the diameter.
Thermal inertia is odd, right? Because the binaries are thought to be formed by spin-up, shedding of mass.
Mm-hmm.
It's very loose regolith.
Well, that's potentially odd, yes. But the weakness that's involved in having a rubble pile doesn't mean that it's not made out of rocks that are not compacted together. And the scale on which we're measuring this is like 10 centimeters. So you could easily have a rubble pile that's a bunch of 1 meter boulders that spun up and then flew apart and then coalesced into 1 meter boulders. And then when you're looking at the surface, you're seeing the boulders, the thermal behavior of the boulders. So it's hard to know exactly what's going on. But it definitely has a pretty high thermal inertia. You can see that we observed it from very different spots in the Earth's orbit here with October, April, and October. So that lets us figure out which way it's spinning and how much the morning-afternoon asymmetry is. So I brought up 2010 MU112. So it's in a sort of 7-to-3 resonance with the Earth, not exactly. So that meant 7 years later of the Earth, it's 3 orbits for 2010 MU112. So it's back more or less where WISE can see it. So I stacked the images. There it is. Now it's in the galactic plane. WMAP did not report this. It had previously been seen in 2017 by Spacewatch observers at Kitt Peak. So we have a very good idea of where it was supposed to be. This thing here is exactly on the predicted position. So that means we can use that data to try to repeat the thermal modeling. So when we first detected it, we had 12 and 22 microns going. Second detection, only 4.6 and 3.4. So we get slightly different parameters, but not very much. So this particular model that's best fit during a Monte Carlo Markov chain is about 2.5% albedo. Okay, so Jean-Luc Margot will, of course, remember why I'm talking about Icarus. So we were both on Adam Greenberg's thesis committee, and one of the experiments he reported on was radar observations of Icarus. And one of the things he compared his data to was previous measurements in the infrared. So in 2010, we saw 1.36 kilometers, and in 2014, 1.03 kilometers, and then Adam's radar result was 1.44 plus or minus 0.26 kilometers. So not really high quality radar data, but I was interested in knowing exactly what the infrared data show. And so I went scanning through the archive, and this is all publicly available. Any graduate student who's interested in doing a thesis, the data is taken, it's on the ground. It's pretty easy to find these things too. So it turns out that we saw Icarus during the cryogenic mission when the 22 micron channel was going. It was further away than for this, so it's low signal noise, but you can stack the images and get these values. And then this is the previously reported result, and here's another previously reported result. And then during the same pass where the radar observations were made, we scanned over Icarus once. It was moving across the sky quite fast. So we got an observation then. Notice it's very bright. And then later that year, we scanned over Icarus again, but it was pretty far away. So we have to stack images. We only get this value at W2.
Ned, there are probably people in the audience who don't know that 7.51 is very bright. I'm not going to just mention that.
Well, these are magnitudes. Anyway, yeah, you're right. So 7.51 is brighter than, this is 100 times brighter than this.
Why are there no W1, W2 measurements in the cryo phase?
Because this time it was so far away that it's too faint. I looked, there just wasn't any worthwhile data then. So we can do the map. We actually solve for where the rotation pole is. Luckily for radar, it's exactly where the radar said it was. And then we can solve for a model. This is the best fit model to all this data. It's now a 10 parameter fit because we throw in the axis ratios of a triaxial ellipsoid model. And then the volume effective, equivalent effective diameter is 0.98 plus or minus 3.5%. So that's 2 sigma lower about than the recent radar observations. Anyway, that's Icarus. So now on to NEOCam. This is our proposal. Now the proposal is a bigger telescope with a much bigger array, so it covers about 12 square degrees, and it's much more sensitive. So the purpose is to find, track, and characterize all the small bodies.
Excuse me, how is this thing passively cooled?
You just don't point at the sun, and you're out in space, then you cool off. So,
Well, that sounds
so that's the passive cooling. Don't point at the sun. And the so we're really planning the survey to find the NEOs. So for WISE, it was kind of parasitic observations to find the NEOs and separate them out from the celestial things. So we expect to find 100,000 new NEOs and millions of main belt asteroids. And then we obviously have to track all the moving objects. So even though they're main belt and won't hit us, we do want to see them. So this is where NEOCam sits, a little bit inside the Earth's orbit. And then it scans this big cone. And then 6 days later, it comes out and scans this big cone. And then it scans this big cone again, and back and forth. And this little narrow cone is what WISE covered. So it's a much bigger area, it's much more sensitive. And we can actually detect, well, with favorable thermal properties, 140 meter NEO at 1 astronomical unit distance. So we'll see them lots of times. And these are the detectors we've been working on. So they work fine at 40 Kelvin. And the Spitzer Space Telescope running warm is down around 30 Kelvin. So it looks like we can operate these 10 micron detectors with a passively cooled telescope. And this shows what we could do with NEOCam. Here's sort of the expected trend in fraction of the 140 meter NEOs. So right now we're at about 30%, 30-some percent. But with ground-based surveys, we'll keep going. But if we put in NEOCam, we could find most of them rather quickly. And LSST, on the other hand, could greatly improve the rate of finding NEOs. But you'll notice it's kind of asymptoting up here at about 75%, which is, by coincidence, no doubt, just the fraction of the NEOs that have the bright albedo. So they're not going to find the dark ones very well. And that's because if we have a 140 meter NEO at 1 AU distance, 90 degree elongation, just to be specific, using the NEDM with 8 equals 1, NEOCam can see it at 8 microns or in the 6 to 10 micron band. Won't really detect it, but can measure it at 4.6 microns. LSST, on the other hand, can see that one if it's got a high albedo, but only if it's in the green or red filter. So it actually plans to do all its surveying in around about Lazy Susan, switching out of 5 different filters. So only 40% of the time will it be observing in a band that's sensitive, particularly to NEOs. Some time spent in ultraviolet is just going to be a total loss for NEOs. Anyway, so you can't use LSST to find these coal black objects very well. And then I'll just spend a little time talking about how we measure diameters. So one way of looking at it is if you could find out the total light that's reflected by the asteroid and the total light that's absorbed and re-emitted in the infrared by the asteroid, and compare that to the flux from the sun, you can figure out the diameter. And there's no ifs, ands, or buts. So to do that, you need to have bolometric detectors, little thermometers sitting in the focus of a camera all around the asteroid, all at the same time, which we never have. But in principle, if you had that, we get perfect diameters. What we usually have is one detector in one spot looking through one filter at the asteroid. So that's not so good. We need a model to figure it out. What do we need to figure out? We need to figure out the phase integral, which is the integral over all phases compared to the actual emission at the phase we observed. So we need the phase function over the, well, the phase integral over the phase function. And, you know, there's a variety of models. They're not too different, actually, plus or minus 20%. And then we need bolometric corrections. That's the total flux divided by the flux we observe. Not too uncertain. Again, plus or minus 20% in the main belt. Not so bad at 1 AU. This is for NEOCam. And so basically this factor is the optical to infrared ratio. And that can be estimated to about 5% even without any optical data. This is estimated to 20%, 20%, and this is known to 10% or better because it's a detection. So you end up with diameters that are good to 15% or better. And that's what we see with WISE. So just using only W3, no optical data, no nothing, we get diameters that agree with the radar or occultation or spacecraft measurements within 15%. And NEOCam can do better than that because we have multiple observations because we observe things so far away. So by the way, this little gray piece here, over here, that's what 17% albedo looks like. And unless you're up close, maybe you can't even see that it's not black. So that's black. That's what a bright reflective asteroid looks like. So NEOCam has two colors, which is better. We'll observe multiple phases, but not at the same time. And so then we can do a better model. So I'll just conclude by saying that infrared observations are a great source of information about cool objects like asteroids. And advances in detectors over the past 10 years have made it practical to build an observatory in space that can last for years and find and study millions of asteroids. And so we could actually do what Congress told NASA to do a long time ago, get to 90% of all objects with diameters greater than 140 meters. That is often corrupted by LSST to be absolute magnitudes brighter than 22, but that's a corruption. Congress doesn't care about the absolute magnitudes. They only care about the diameters and the damage. So anyway, I think I'll stop there and take questions.
Time for a few, Jane.
You started off to look for some other bodies, and you found only asteroids.
We started off to look for the closest stars to the sun with WISE and the brightest galaxies in the universe and asteroids. So we found all of those. So we found a lot of it.
You say?
Yeah, we found a galaxy that's got a luminosity of, you know, about 5 times 10 to the 14 solar luminosity, so 500 trillion solar luminosity. And we found stars that are 2 parsecs from the sun. Not quite closer than Alpha Centauri, but pretty close.
How do you guys handle the enormous amount of data that come out? I mean, it's
Well, we use computers, Bill. We use computers.
Oh, I'm sure, but then, you know, I mean, it's, I think you need a cast of thousands of people working on it.
Well, actually,
Hundreds anyway.
you know, we're trying to use computers more. So when if we get NEOCam going, it will be finding, you know, probably 50 times more potential tracks, you know, what looks like 4 dots in a row moving in a straight line at constant velocity across the sky. And so we're going to be seeing how well we can get computers with machine learning to actually decide whether these are reasonable or crap. For WISE, we just have people look at them.
Is this going to be a NASA-funded project?
This is NASA funded, but I'm sure,
Can't you get money from the military instead?
well, yeah, yes, I suppose.
It'd be better if we had, and let NASA save their money for other projects. If anything wrong with yours, it's just you might as well get more money, it's not a zero-sum game, then if you
Yeah,
get some money.
not a zero-sum game, but anyway, Congress told NASA to do this, they didn't tell the military to do it.
More questions? It is somewhat late. So we're not inviting you to lunch today?
Yeah, I have to go off, I got something to do in the afternoon.
Well, we have to eat, I mean, if you got him, I mean, okay, so he's a photo trope.
I've got some stuff in my refrigerator if you want to come along. Okay, thanks again.